We've spent quite a bit of time trying to find the volume of curves rotated around the x-axis. Today we're going to take a look at working in 1 dimension and also 2 dimensions, the surface area. We're going to answer the question, how do we find length and surface area? First, we're going to start by finding arc length. And we're going to start by setting up the idea behind what we're doing. I'm going to kind of oversimplify this just a bit, just to make a point of how this works. So if we've got some curve on here, if the curve is really windy, let's make it a little more windy than that. If the curve is really windy, it's difficult to actually measure how long that curve is. Well, one way we could estimate it is by drawing tangent lines that connect pieces together. And each of those tangent lines being straight can be measured a lot easier. In fact, if we pick one of those tangent lines and we zoom in on it, so that's the same tangent line zoomed in on, we'll notice that there is some distance of change in x. Maybe we'll call it dx. And some vertical distance that's the change in y. We'll call that dy. Well, we know from the Pythagorean theorem that the hypotenuse, that length we're looking for, is equal to the square root of the first leg squared, dx squared, plus the second leg squared, dy squared. And I want to play with this formula just a little bit to make it a little more user-friendly to us. First thing I'm going to do is I'm going to factor out a dx squared from the expression. When I factor a dx squared out of the first term, we get 1, plus when we factor a dx squared out of the second expression, we get dy dx squared. And this simplifies a little nicely because the square root of dx squared is just dx. And so what we have left under the square root is 1 plus, and you notice we have this dy dx. Well, dy dx is just the derivative, f prime squared. Well, that's the length of just one of the little tangent lines. If we wanted to get the length of all the tangent lines all together, we would need to add the pieces together. We would have to integrate all the individual ones. So all together, the arc length is equal to the integral from our lower limit of a to the upper limit of b, from a to b, of the square root of 1 plus the derivative of the function squared dx. It doesn't really look like a 2 on there. That's a 2. So this is going to be our general formula to find the length of any curve. So now that we have a nice little formula, the integral of the square root of 1 plus the square of the derivative, let's see if we can do a couple examples. Starting with f of x equals 4/3 x to the 3/2. And we're going to find its arc length between 0 and 1. Well, our formula, it's just off the screen here. Let me bring it back. Our formula says that arc length is going to be the integral from 0 to 1, those limits, of the square root of 1 plus the derivative squared. Let's come over to the side and see what the derivative is then. The derivative is 4/3 times, bring the exponent out front, 3/2, x to the, reduce the exponent by 1, 1/2. And that's nice because the 3's divide out, and 4/2 is 2. So really, the derivative is 2x to to the 1/2. So that's the function, the derivative of the function, 2x to the 1/2. And we're going to square it dx. Well, if I actually do that square, we get the square root of 1 plus 2 squared is 4. X to the 1/2 squared is x dx. And that gives us an integral we should be very comfortable solving using u substitution, where u is 1 plus 4x, and du is just 4 dx. So we're going to multiply by 4 inside and 1/4 outside. So we have 1/4 times the integral. Let's plug the limits of integration into our u. We plug 0 in. 1 plus 0 is 1. We plug 1 in. 1 plus 4 is 5. So we're integrating from 1 to 5 of the square root of u, or u to the 1/2 du. So that gives us 1/4 times u to the 3/2 times 2/3 integrated from 1 to 5. Let's go ahead and multiply the constants together. So we end up with 2/12 times 5 to the 3/2 minus 1 to the 3/2, which is just minus 1. And 2/12 we can actually reduce down to 1/6. So let's go ahead and do that. So we have 1/6 times 5 to the 3/2 minus 1. That is going to give us the length of the arc, 4/3 x to the 3/2 between 0 and 1. That's the length of that curve. We can also do this using our y's, much the same idea. Let's say we've got the function g of y equals y cubed over 3 plus 1 over 4y. Now, one thing you notice right away is we're going to need to bring that y, make it more user-friendly. So I'm going to rewrite this as y cubed over 3. Actually, let's even make it 1/3. 1/3 y cubed plus 1/4 y to the negative 1. Because we know we need the derivative of this function in order to find the arc length. Oh, I didn't give a distance. Let's give the distance. Let's find it between, let's go from 1 to 3. And that would be the y's. Y's going from 1 to 3. So now to take the derivative, because we need that in our formula, we bring the 3 out front and it reduces. So we're just left with y squared. Plus, bring the negative 1 out front, makes it minus 1 over 4 y to the negative 2. Let's do some algebra and actually move that y to the negative 2 into the denominator. Y squared minus 1 over 4y squared. And let's actually make this into one big fraction by multiplying the left part by 4y squared over 4y squared. And that'll give us 4y to the 4th minus 1 over the common denominator of 4y squared. Now let's go to our arc length formula. We're doing it with y's. That's OK. We're going to integrate with respect to y. We're going to integrate from 1 to 3 of the square root of 1 plus the 4y to the 4th minus 1 over 4y squared squared dy. Here's where the algebra becomes very helpful, because this is going to simplify quite nicely for us. First, when we square, we get the integral from 1 to 3 of the square root of 1 plus. Squaring the numerator will give us 16y to the 8th minus 8y to the 4th plus 1 over Squaring the denominator gives us 16y to the 4th dy. Let's get this all under a common denominator. So we're going to multiply the 1 by 16y to the 4th over 16y to the 4th. And that gives us the integral from 1 to 3 of the square root of 16y to the 4th plus 16y to the 8th minus 8y to the 4th plus 1 over 16y to the 4th dy. Combining like terms on those y to the 4ths, we get the integral from 1 to 3 of the square root of 16y to the 8th plus 8y to the 4th plus 1 over 16y to the 4th dy. We're almost done with our algebra. Still integrating from 1 to 3, that numerator can factor. It's actually a perfect square. Perfect squares are what we're looking for because we can take the square root of a square really easy. 16y to the 8th, the square root of that is 4y to the 4th plus 1 squared all over 16y to the 4th dy. And that is really nice because we can take the square root of the numerator and denominator. So we're integrating from 1 to 3. The square root of a square is just the stuff, 4y to the 4th plus 1, over the square root of 16 is 4, and the square root of y to the 4th is y squared, dy. Almost to the point where we can do some calculus. We're integrating from 1 to 3. Let's divide both parts by the 4y squared, and we end up with y squared plus 1/4 y to the negative 2 dy. These problems often require a lot of algebra to get us to a point where we can actually take the integral. Don't be afraid to mess with the algebra, work with it, and get us something that we can actually take the integral of. This integral is actually really easy to take. It's y cubed divided by 3. We're going to subtract because when we increase the exponent by 1, we get y to the negative 1 over 4, integrated from 1 to 3. And I'm actually going to write that a little nicer, y cubed over 3 minus 1 over, let's bring the y down, 1 over 4y integrated from 1 to 3. Plug in the limits of integration. 3 cubed is 27, divided by 3 is 9, minus 1 over 4 times 3 is 12, minus, plugging the 1 in gives us 1/3, plus, plugging the 1 in gives us 1/4. And this simply plugs into our calculator. 9 minus 1/12 minus 1/3 plus 1/4 gives us a total length of 53/6. Again, the integration is really simple, just using the formula. There's might be some algebra you need to do, though, to get yourself all the way through to a point where you can take the integral. So that's arc length. To find the arc length, we just take the integral from a to b of the square root of 1 plus the derivative squared dx. The other half of the question, though, was how do we find surface area? And again, we're going to set surface area up with the idea behind what we're doing. So let's say we have some function, some curve. And we're going to rotate it around the x-axis. And we want the surface area of that shape. Up to this point, we've spent a couple days doing the volume of that shape using shells, disks, and washers. Now we want the surface area. We don't want to fill it with paint. We want to paint the outside. Well, similarly, though, we're going to take a cut out of it. Small little cut out of it. And when we lay it out flat, that ends up being a cylinder. And if I were to slice that cylinder and open it up, we end up with a rectangle. It's a two-dimensional rectangle because we're dealing with just the surface area, not the thickness. We don't care about the thickness. Now, the dimensions on this rectangle are interesting. First, let's take a look at this little thick piece. That thickness that we're looking at is really a piece of the entire arc length. So that height is really a piece of the entire arc length. The height of this rectangle is going to be the arc length as it goes across. The radius of this circle is simply the function, f of x. The base of this rectangle, then, is the distance around the circle as we open it up. That's the circumference, which is 2 pi times the radius of f of x. So if we put it all together, the surface area of just this piece is going to be 2 pi times f of x, the length, times the height, which is the piece of the arc length. Now, we want all of the surface area pieces, the entire surface area. So again, we're going to integrate from a to b to get all the pieces added together of 2 pi times f of x times the arc length. Well, 2 pi is a constant, so we can pull that out front. So the surface area is the 2 pi times the integral from a to b of f of x times our arc length. And this is the formula we've been using thus far. We already have it. It's 1 plus the derivative squared dx. And so this formula becomes the formula for the surface area of a curve rotated around the x-axis. And if we rotate it around the y-axis, we would just switch all the x's for y's and do it with respect to y. So if that's our formula, let's do some examples to see if we can use this formula. See if I can leave the formula on the screen. See if I have enough space. Let's let f of x equal the square root of 1 minus x on the interval from 0 to 1/2. And we're going to rotate on the x-axis. We're going to find the surface area. Well, we know from our formula we don't just need the function, we also need the function's derivatives. So let's find those pieces first. So the function f of x is 1 minus x to the 1/2 power. Its derivative is, bring the 1/2 out front, times 1 minus x to the negative 1/2 times the derivative of the inside, which is negative 1. So let's write that as negative 1 over 2 times 1 minus x to the 1/2 power. Now we're ready to plug it into our formula for surface area. It's equal to 2 pi times the integral from our limits of 0 to 1/2 of our function, 1 minus x to the 1/2, times the square root of 1 plus the derivative, which is negative 1 over 2 times 1 minus x to the 1/2 squared dx. This integral is very easy to take. The algebra to get there will require some digging, though. So let's dig into this algebra. First, let's square that derivative. So we have 2 pi times the integral from 0 to 1/2 of, let's change this back to a square root. It's going to actually be easier that way later. Times the square root of 1 plus negative 1 squared is 1. 2 squared is 4. And when we square the 1/2 power, we're just left with 1 minus x dx. Let's do the common denominator thing again. I'm going to multiply by 4 times 1 minus x on top and bottom so that we can have a common denominator and write that out. When we do that, we get 2 pi times the integral from 0 to 1/2 of the square root of 1 minus x times the square root of, I'm going to go ahead and distribute. So we have 4 minus 4x plus 1 over our common denominator of 4 times 1 minus x dx. Continuing to simplify, we've got 2 pi times the integral from 0 to 1/2 of the square root of 1 minus x times, let's break that square root in top and bottom. 4 plus 1 is 5 minus 4x over, on the bottom, the square root of 4 times 1 minus x dx. And this is going to start to become really nice because we've got a 1 minus x under a square root and a 1 minus x under a square root. Those will divide out. Square root of 4 is 2. So I'll pull a 2 out. But that's really nice because we've got a 2 on top and a 2 on bottom. So those all divide out. So with all that said, our integral simplifies down to pi times the integral from 0 to 1/2 of the square root of 5 minus 4x dx. That's the algebra needed to get us down to an integral we can actually take. We're going to use u substitution of 5 minus 4x du is equal to negative 4 dx. So we'll multiply by negative 1/4 outside and negative 4 inside. And now we have negative pi over 4 times the integral. Plugging 0 in for u. 5 minus 0 is 5. Plugging the 1/2 into the u equation. 4 times 1/2 is 2. 5 minus 2 is 3. And we're just left with u to the 1/2 du. Seems like my integration's backwards between the 5 and the 3. So let's switch them. Remember, we can switch them as long as we change the sign on the outside. So we'll make it a positive pi over 4 times the integral from 3 to 5 of u to the 1/2 du. Integrating, we get u to the 3/2 times 2/3. Integrated from 3 to 5. 2 over 4 will reduce with a 2 in the denominator. So we're left with pi over 3 times 5 to the 3/2 minus 3 to the 3/2. And this will be the surface area of our curve between 0 and 1/2 when it's rotated around the x-axis. Let's wrap up with one more example. This time we're going to rotate on the y-axis and see how that impacts things. Let's say our function is f of x equals the square root of 9 minus x squared. And x is going to run from the square root of 5 to 3. And we're going to rotate on the y-axis. And that's significant because if we rotate on the y-axis, we have to take the derivative with respect to y. Basically, the only extra step we have is to convert everything into y's. So let's start with, we've got x equals the square root of 9 minus, I'm sorry, not x equals, y equals 9 minus x squared. If we square both sides, we get y squared equals 9 minus x squared. Add x squared to both sides, subtract y squared from both sides, and then take the square root, we get 9 minus y squared. It's basically the same function, which is kind of interesting. To get our limits, we're going to plug the square root of 5 in for our x. So we get the square root of 5 squared is 5. 9 minus 5 is 2. We'll plug the 3 in. 3 squared is 9. That goes to 0. And let's just put them in order. We're really integrating then from 0 to 2. We still need to know the derivative of our function so that we can plug it into our equation. So we've got x prime, the derivative is 9 minus y squared to the negative 1/2, pulling the 1/2 out front, times the derivative of the inside, which is negative 2y. It's nice because the 2's divide out, not the y's. So when we simplify, we're left with negative y over 9 minus y squared to the 1/2 power. There's our derivative. OK, we have the pieces we need. Now we're ready to go after the surface area. Surface area is 2 pi times the integral from 0 to 2, we said, of our function. That's the square root of 9 minus y squared times the square root of 1 plus the derivative squared. So let's write out every step here. Negative y over 9 minus y squared to the 1/2 squared dy. And this is the integral we need. Again, the algebra is going to take some work. This integral is even easier than the last one to actually evaluate. But we have to do a little bit of algebra to clean it up to make it like we want. So let's work with it. We have 2 pi times the integral from 0 to 2 of the square root of 9 minus y squared times the square root of 1 plus, let's go ahead and square. We've got y squared over 9 minus y squared. Let's do that common denominator thing again by multiplying by 9 minus y squared on top and bottom. Oops, I forgot the dy. So now that's equal to 2 pi times the integral from 0 to 2 of the square root of 9 minus y squared times the square root of 9 minus y squared plus y squared over our common denominator of 9 minus y squared dy. Cleaning up, we have 2 pi times the integral from 0 to 2 of a square root of 9 minus y squared times, notice the y squares divide out, or subtract out. Negative y squared plus y squared is 0. We're just left with the square root of 9 on top, which is 3, over we've got a square root of 9 minus y squared in the denominator, dy, which is really nice because that square root divides out. And so the integral we're actually going to take is 2 pi times the integral from 0 to 2 of 3 dy. That integral we can take really quick. It's 2 pi times 3y integrated from 0 to 2. Or 2 pi times 3 times 2 is 6 minus 0. We are left with a surface area of 12 pi. So what you start to notice with these problems, both surface area and arc length, the integration step's quite simple, but we'll have to work with the algebra inside that formula to get it to a spot where we can take an integral a bit nicer. All right, take a look at the homework assignment. We're doing surface area formula and the arc length formula. Practice a few of these, and we will discuss these in more detail in class.